So particle of mass m kilograms, one end of a light elastic string, and other end of fixed O. So we've got O here, we've got particle here, and it's on a smooth horizontal surface. So that's my particle P, and it's connected by a string like so. And we've got lambda equals 1.35 mg. We've got natural length 1.8, and mass is m, so mg, and we got tension, which equals lambda x over L. Lambda's that, and that's L there. It's held at rest at a point 3 meters from O, so this distance, it's obviously not to scale, is 3, and so this distance here is going to be 1.2 meters to get up to the right distance. And it's released. Find the initial acceleration of P. Well, for the only thing which links, we've got forces and acceleration, is obviously going to be resultant force equals mass times acceleration. I should have acceleration here. Let's put it on going that way, because it will be accelerating that way. And we're going to get resultant force, and we're going to resolve in the direction of the acceleration, take that to be positive. So we got T, which is lambda, that's 1.35 mg, lambda x, the extension, which is 1.2, divided by L, which is the natural length, 1.8. That is the resultant force. There's no other force in there. There's no friction because it's a smooth horizontal surface. And that equals mass, which is m times by the acceleration. That's what we want to find. And so m's cancel out. And so A equals that bit there. And that gives me that A equals 8.82 meters per second squared. It's done the first thing. And now we're going to do the second bit. We'll do it up here. The speed at the instant the string becomes slack. So I want to, it's released from this point here, and I want to know how fast it's going at the moment it becomes slack. Well, it's going to be an energy thing. So we have total initial energy equals total final energy. And what have we got to start off with? We've got three possibilities. We've got elastic potential energy, we've got gravitational potential energy, and we've got kinetic energy. And we're going to get the same thing over here. Elastic potential energy plus kinetic energy, don't need different, plus gravitational potential energy. And it's all on the same slope, so that's going to be 0 at the mgh. And it's released from rest, so the kinetic energy is going to be 0, and the final elastic potential energy is going to be 0, and we're going to get a half mv squared is what it's going to turn into. We have to work out what the elastic potential energy, and that's going to be lambda x squared over 2L. We need that formula. And so what's lambda? So that is 1.35 mg times by the extension squared, so that'll be times by 1.2 squared all over 2L, so that's 2 times 1.8, and that is the elastic potential energy, and that's going to equal half mv squared. M's cancel out, times both sides by 2, we'll get rid of that, and that says that v squared equals 10.584, and so v equals 3.25 meters per second. And that's a fairly straightforward thing. It does, of course, highlight that we must know elastic potential energy formula and tension formula. And that's one done.